In the depths of space, astronomers just shattered every measurement we thought we knew about reality itself. The universe we live in is 93 billion light-years across, contains over 2 trillion galaxies, and holds structures so massive they span 4 billion light-years. But here is what will blow your mind. Recent discoveries suggest the actual universe could be 250 times larger than what we can see, while new measurements show we might have been wrong about its size by millions of light-years. If you are enjoying this journey through cosmic measurements, give this video a like. Prepare yourself for the most mind-bending size revelation in scientific history. Henrietta Swan Leavitt stared at her photographic plates in 1908, completely unaware she was about to destroy everything astronomers believed about the size of existence. Working as a human computer at Harvard Observatory, Leavitt noticed something strange about certain stars in the Magellanic Clouds. These stars pulsed with perfect rhythm, like cosmic lighthouses flashing across impossible distances. What she discovered would eventually prove that our entire galaxy was just a tiny speck in an ocean of space so vast it defied human comprehension. The stars she studied were Cepheid variables, massive suns that expand and contract in precise cycles. Here was the key insight that changed everything. The brighter these stars actually were, the slower they pulsed. This meant astronomers could determine their true brightness just by timing their flicker. Once you know how bright something really is, of billions of stars, located millions of light-years beyond the edge of the Milky Way. In 1925, Edwin Hubble used Leavitt's method to prove that the Andromeda Galaxy sat 2.5 million light-years from Earth. The known universe suddenly expanded from 100,000 light-years across to over 5 million light-years in diameter. It was like discovering your backyard actually contained an entire continent. This was just the beginning of a measurement revolution that continues today. Each new discovery revealed that the previous estimate of cosmic size was laughably small. The universe kept growing in our understanding, from millions to billions to trillions of light-years. Modern telescopes now reveal galaxies so distant their light began traveling toward us when the universe was barely 300 million years old. These ancient beacons shine from distances that stretch our ability to comprehend scale. If the Milky Way were the size of a dinner plate, the observable universe would be larger than North America. The most mind-bending part is that everything we can see might represent less than 4% of what actually exists out there. Dark matter and dark energy, invisible forces we barely understand, appear to dominate the cosmic landscape. We are like insects trying to map an entire planet while sitting on a single grain of sand. Recent measurements, using the most advanced instruments ever built, suggest our previous calculations might still be wrong. The observable universe could be slightly smaller than we thought, or the actual universe could be hundreds of times larger than the portion we can detect. However, before we can grasp these impossible scales, we need to understand something even more basic about our place in this cosmic vastness. Every night when you look up at your bedroom ceiling, you are staring through more empty space than the greatest minds in history believed could possibly exist in the entire universe. Ancient Greek astronomers thought the cosmos was a series of crystal spheres rotating around Earth, with the outermost sphere containing all the stars just a few thousand miles above our heads. Aristotle calculated that the entire universe could fit inside a ball roughly the size of our solar system. He was off by a factor of trillions. Even as recently as the early 1900s, astronomers believed the Milky Way represented the complete universe. They thought it measured about 30,000 light-years across, making it seem impossibly vast at the time. To put this in perspective, they believed all of existence was smaller than the distance between Earth and just our closest neighboring galaxies. Your bedroom ceiling sits roughly 8 feet above your head. The space between your pillow and that ceiling contains the same proportion of emptiness that exists between galaxies in the observable universe. If you scaled down the cosmos until galaxies were the size of marbles, the average distance between them would be about 20 feet. Your bedroom is actually a pretty good model of cosmic spacing. This realization helps explain why ancient astronomers made such dramatic underestimates. They could see individual stars with the naked eye, so they assumed the star-filled sphere must be relatively close. They had no way to detect the vast gulfs of nearly empty space that separate stellar neighborhoods. The breakthrough came when astronomers finally measured the distance to a single star using parallax. This technique works like closing one eye, then the other, and watching how nearby objects appear to shift against distant backgrounds. Earth's orbit around the Sun provides a 600 million-mile baseline for these measurements. Friedrich Bessel succeeded in 1838, determining that the star 61 Cygni lay 11 light-years from Earth. That single measurement revealed more empty space than ancient cosmologists thought could exist anywhere. One star, sitting in what they considered nearby space, was actually farther away than their estimate for the size of everything. Modern measurements show that the observable universe contains roughly 10 to the power of 82 atoms spread across a sphere 93 billion light-years in diameter. If you could somehow collect every atom in the observable universe and spread them evenly throughout that volume, each atom would be separated from its nearest neighbor by about 3 feet. The cosmos is almost entirely empty space, punctuated by rare islands of matter. This emptiness creates one of the most counterintuitive aspects of cosmic scale. When you look up at a star-filled night sky, you are seeing an incredibly dense concentration of matter. The view from Earth toward the galactic center shows thousands of stars in a single field of view, yet each of those stars is separated from its neighbors by distances so vast that light takes years to cross between them. But even this perspective fails to capture the true strangeness of cosmic measurements, because the tools astronomers use to measure these distances themselves reveal something impossible about the nature of space and time. The James Webb Space Telescope achieved something that should be physically impossible. It photographed galaxies that formed before the universe was old enough for such galaxies to exist. Floating 1 million miles from Earth at a gravitational balance point, this 21-foot-wide mirror collects infrared light that has been traveling through space for over 13 billion years. When astronomers processed the first deep-field images, they discovered fully formed galaxies shining just 290 million years after the Big Bang. Here is why this discovery broke the rules of cosmic evolution. Galaxies, this early in universal history, should not have had enough time to grow so large and organized. It takes hundreds of millions of years for gravity to pull together the raw materials needed to build the first massive stars. Those stars must then live their entire lives, explode as supernovae, and scatter heavy elements through space before second-generation stars can form planets and more complex structures. Think of it like finding a fully constructed skyscraper in a city that was founded last week. The materials, construction time, and organizational complexity required should have taken much longer than the available time frame allowed. The James Webb Telescope can see these impossible galaxies because of a quirk in how light behaves across cosmic distances. As the universe expands, the wavelengths of light get stretched like a rubber band being pulled from both ends. Light that started as visible blue and white colors gets stretched into infrared radiation by the time it reaches Earth. This stretching effect, called redshift, turns distant galaxies invisible to human eyes and optical telescopes like Hubble. James Webb was specifically designed with infrared sensors to detect this stretched ancient light. It can observe galaxies whose light has been traveling toward us for over 99% of the universe's current age. The telescope's sensitivity is so extreme that it could detect the heat signature of a bumblebee orbiting Jupiter. This precision allows it to study individual galaxies that formed when the universe was just 2% of its current age. These primordial galaxies appear surprisingly bright, massive, and well organized for such early cosmic times. One galaxy, designated JADES GS Z140, appears to contain billions of stars and shows signs of active star formation, despite existing when the universe was barely 400 million years old. The galaxy is so luminous that it suggests star formation was proceeding much more rapidly in the early universe than current theories predict. Even more puzzling, some of these early galaxies contain supermassive black holes with masses equivalent to millions of suns. Black holes this size should require hundreds of millions of years to grow through gradual accumulation of matter. Finding them in such young galaxies suggests that either black holes formed much more quickly than expected, or the universe underwent periods of accelerated development that we do not yet understand. The James Webb Telescope has also detected carbon, oxygen, and other heavy elements in galaxies formed less than 500 million years after the Big Bang. This discovery pushes back the timeline for when planets capable of supporting life could have first formed by several billion years. These observations force astronomers to reconsider fundamental assumptions about how quickly cosmic structures can assemble and evolve. The early universe appears to have been a much more active and rapidly changing place than previous models suggested. However, these revelations about early cosmic history pale in comparison to the challenge of measuring something that refuses to hold still long enough to be accurately sized. Imagine trying to measure a balloon while someone continuously inflates it, and you begin to understand the fundamental problem astronomers face when determining the size of the universe. Every measurement technique used to gauge cosmic distances must account for the fact that space itself expands while light travels from distant objects to our telescopes. A galaxy that was 46 billion light-years away when it emitted the light we see today is actually much farther from us by the time that light reaches Earth. This expansion creates a mind-bending paradox. We can observe galaxies whose light has been traveling for over 13 billion years, suggesting they should be 13 billion light-years away. However, due to cosmic expansion during that light travel time, these same galaxies now sit roughly 46 billion light-years from Earth. The observable universe has a radius of 46 billion light-years. Despite being only 13.8 billion years old, the expansion rate is not constant throughout space or time, making measurements even more complex. Edwin Hubble discovered that more distant galaxies recede from us faster than nearby ones. This relationship, called Hubble's law, shows that cosmic expansion accelerates with distance. A galaxy twice as far away moves away from us twice as fast. Current measurements indicate that space expands at roughly 70 kilometers per second for every megaparsec of distance. This means that 2 points in space separated by 3.3 million light-years will move apart at 70 kilometers per second due to expansion alone. Over cosmic distances, this expansion can cause galaxies to recede faster than the speed of light. This creates an observational horizon beyond which we can never see, no matter how powerful our telescopes become. Light from galaxies beyond this horizon is fighting a losing battle against the expansion of space itself. Like a person running on a treadmill that speeds up faster than they can run, the light from the most distant galaxies can never reach us. The expansion also means that galaxies we observe today will eventually disappear from view. In roughly 2 trillion years, cosmic expansion will carry most galaxies beyond our observational horizon. Future civilizations will look out at a nearly empty universe, with only the local group of galaxies remaining visible. Even more puzzling, the expansion rate appears to be accelerating due to a mysterious force called dark energy. This force makes up roughly 68% of the universe and pushes galaxies apart with increasing strength as the universe ages. Dark energy was discovered in 1998 when astronomers studying distant supernovae found that the universe's expansion was speeding up rather than slowing down as expected. Measuring cosmic distances while accounting for this accelerating expansion requires sophisticated corrections to observational data. Astronomers must calculate not just where an object was when it emitted light, but where it is now, where it will be, by the time we point our telescopes at it, and how the expansion rate has changed over the light travel time. The most distant galaxy ever observed, JDES GSZ 14-0, appears to us as it was just 290 million years after the Big Bang. By the time its light reaches Earth, cosmic expansion has carried it to a distance of over 33 billion light-years. The galaxy has aged another 13.5 billion years. While its light traveled to our telescopes, this constant cosmic motion makes every distance measurement a snapshot of a universe that no longer exists in the configuration we observe. We are always seeing the past, never the present state of distant cosmic structures. Yet, despite these complexities, astronomers have identified specific markers in space that allow precise distance measurements across these vast, expanding scales. In the constellation Cygnus, a star called 61 Cygni became the first cosmic landmark to prove that the universe has boundaries we can never cross, no matter how long we travel or how advanced our technology becomes. Friedrich Bessel measured the distance to this unremarkable star in 1838, using a technique that would revolutionize astronomy and ultimately reveal the edge of everything we can ever hope to observe. His measurement of 11 light-years marked the beginning of our understanding that the cosmos has a finite observational boundary. Bessel used stellar parallax, watching how the star appeared to shift position as Earth moved from one side of its orbit to the other 6 months later. This shift measured just 1/3 of an arcsecond, an angle so small it equals the width of a dime seen from 2 miles away. Yet this tiny measurement opened the door to understanding cosmic scale and the fundamental limits of observation. The breakthrough revealed something profound about the nature of space and light. Since light travels at a fixed speed of 186,000 miles per second, there exists a maximum distance from which light can reach us during the universe's lifetime. This creates a sphere of observability surrounding Earth, with us at the center, not because we are special, but because we are the observers. This observational sphere has a radius of roughly 46 billion light-years in all directions, creating the observable universe with a diameter of 93 billion light-years. Beyond this boundary lies the cosmic horizon, an edge as real and impassable as the horizon on Earth's oceans. No telescope will ever see beyond it, regardless of technological advancement. The cosmic horizon works differently than Earth's horizon. However, on our planet, you can travel toward the horizon and reveal new landscapes beyond it. In space, the cosmic horizon represents light that has not had enough time to reach us since the universe began. Even if you could travel faster than light toward this boundary, you would never catch the retreating edge of observability. What makes this boundary even more strange is that it surrounds every observer in the universe. An alien civilization in the Andromeda Galaxy sees their own cosmic horizon, centered on their location. Their observable universe overlaps with ours, but extends into regions we can never see. In this sense, every point in space sits at the center of its own observable universe. Recent calculations suggest that the actual universe extends far beyond what we can observe. Statistical analysis of cosmic structure indicates the total universe is at least 250 times larger than the observable portion. Some theoretical models propose the universe is infinite in size, making the observable region an infinitesimal fraction of reality. The cosmic microwave background radiation marks the edge of what we can observe with electromagnetic radiation. This ancient light comes from the moment, roughly 380,000 years after the Big Bang, when the universe first became transparent to light. Beyond this radiation lies the dark age of the cosmos, a period invisible to all forms of electromagnetic observation. Gravitational waves offer the tantalizing possibility of observing beyond the cosmic microwave background, potentially revealing events from the first moments after the Big Bang. These ripples in spacetime travel at light speed, but interact much more weakly with matter than electromagnetic radiation, allowing them to reach us from earlier cosmic epochs. The realization that we live within a bounded, observable universe surrounded by unknowable cosmic realms fundamentally changed how astronomers approach distance measurement. Every technique must work within this finite sphere of observability, calibrated against objects whose light has had time to reach Earth. This observational boundary ensures that some cosmic mysteries may remain forever unsolvable, hidden beyond the edge of space we can never reach. But recent discoveries suggest we may have been measuring even the observable universe incorrectly, making it smaller than we thought by distances that dwarf the size of entire galaxies. In 2024, astronomers made a discovery that shrunk the observable universe by over 190 billion miles, and the evidence came from light that has been traveling toward Earth since before the first stars were born. Scientists Nick Tomasello and Paul Halpern developed new algorithms to analyze cosmic measurements with unprecedented precision. Their calculations suggest the observable universe measures 45.34 billion light-years in radius, rather than the previously accepted 45.66 billion light-years. This difference of 320 million light-years might seem small in cosmic terms, but represents a volume reduction equivalent to removing millions of Milky Way-sized galaxies from existence. The revision comes from more accurate measurements of how fast the universe has expanded since the Big Bang. Earlier calculations relied on approximations that assumed cosmic expansion proceeded at a steady rate over billions of years. However, the universe actually underwent periods of rapid inflation, followed by slower expansion, with recent acceleration due to dark energy. Think of it like calculating the size of a balloon based on how fast you have been inflating it, only to discover that you started with short, rapid puffs, then switched to steady inflation, and recently began inflating faster again. Previous size estimates assumed constant inflation rate throughout the process. The cosmic microwave background radiation provides the key evidence for this revised measurement. This ancient light represents the first electromagnetic radiation that could travel freely through space, released when the universe was just 380,000 years old. By analyzing tiny temperature variations in this radiation, astronomers can determine how much space has expanded since that early epoch. Advanced satellites like the Planck mission mapped these temperature fluctuations with extraordinary precision, revealing patterns that encode information about cosmic expansion history. The data shows that the universe expanded more rapidly in its earliest moments than previously calculated, which means less expansion occurred during subsequent epochs to reach the same present-day size. This discovery highlights the incredible precision required for cosmic distance measurements. The difference of 0.7% in the universe's radius translates to changes in volume calculations that affect our understanding of cosmic structure formation, dark matter distribution, and the total number of galaxies in existence. The revision also impacts calculations about how cosmic expansion will continue into the future. A slightly smaller, observable universe suggests different scenarios for the ultimate fate of cosmic structures over trillions of years. Some models predict that galaxies will eventually become isolated islands in an expanding sea of empty space, while others suggest different timelines for this cosmic isolation. Even more intriguing, the new measurements affect estimates of how much universe exists beyond what we can observe. If the observable portion is smaller than previously thought, and the total universe is a fixed multiple larger than the observable region, then the absolute size of reality itself might be different than current theories suggest. These precise measurements become possible only through careful analysis of light from the most distant observable sources. The James Webb Telescope can now detect galaxies whose light began its journey when the universe was less than 5% of its current age. Each observation provides data points for calculating cosmic expansion rates across different epochs of universal history. The irony is that making the observable universe smaller actually makes it seem more dense with interesting structures. The same number of galaxies, stars, and cosmic phenomena now exist within a slightly more compact volume, increasing the average density of matter and energy throughout space. This measurement precision becomes crucial when comparing our local cosmic environment to the largest structures that span impossible distances across the universe. But these refined calculations pale in comparison to the discovery of cosmic constructions that dwarf human comprehension of what large-scale organization is possible in the universe. Stretching across 1.4 billion light-years of space, the Sloan Great Wall represents the largest single structure ever discovered in the universe, making every human construction project look like an arrangement of atoms by comparison. This cosmic megastructure consists of galaxies, galaxy groups, and galaxy clusters, connected by filaments of dark matter and gas, forming a wall-like barrier that spans roughly 1% of the observable universe's diameter. If you could somehow shrink the observable universe down to the size of Earth, the Sloan Great Wall would stretch from New York to Los Angeles and back again. The structure was discovered through the Sloan Digital Sky Survey, which mapped the positions of millions of galaxies in three-dimensional space. When astronomers plotted galaxy locations, they discovered that cosmic matter is not distributed randomly throughout the universe. Instead, the Great Wall contains an estimated 10,000 large galaxies, each comparable in size to the Milky Way. If every star in every galaxy within this structure were a grain of sand, the total would create a beach stretching from Earth to Mars. The gravitational influence of this structure affects the motion of galaxies across distances that span a significant fraction of the observable universe. What makes these cosmic structures even more remarkable is how quickly they formed in universal history. Computer simulations suggest that structures this large should have required more time to assemble than the universe has existed. The discovery of such massive, organized formations in the early universe suggests that either cosmic structure formation proceeded more rapidly than expected, or our understanding of how gravity operates on cosmic scales requires revision. Even larger structures have been discovered more recently. The Hercules Corona Borealis Great Wall spans over 10 billion light-years, making it roughly twice the size of the Sloan Great Wall. This structure is so large that light takes 10 billion years to cross from one end to the other, representing nearly 3/4 of the universe's current age. These cosmic megastructures challenge fundamental assumptions about how matter can organize itself on the largest scales. According to the cosmological principle, the universe should appear roughly the same in all directions when viewed on sufficiently large scales. Structures spanning billions of light-years seem to violate this principle, suggesting either that the universe is more clumpy than expected, or that we need to revise our understanding of cosmic homogeneity. The existence of such large structures also constrains theories about cosmic inflation, the period of rapid expansion that occurred in the first fraction of a second after the Big Bang. The size and distribution of cosmic structures provide evidence about conditions during inflation and help astronomers understand how tiny quantum fluctuations grew into the massive formations we observe today. Recent discoveries using the James Webb Telescope have revealed that large-scale structures began forming much earlier in cosmic history than previously thought. Observations of galaxies from when the universe was less than 1 billion years old show evidence of organized clustering and filament formation, suggesting that cosmic construction projects began almost immediately after the first stars formed. These vast cosmic structures also play a crucial role in galaxy evolution and star formation. Galaxies located within dense filaments and walls experience different evolutionary pressures than those in cosmic voids, affecting their shape, size, and star formation rates over billions of years. The discovery of these impossible megastructures leads to an even more mind-bending realization about the cosmic inventory. Astronomers have been dramatically undercounting the number of individual building blocks that comprise these vast constructions. Christopher Consolis thought he was conducting a routine galaxy survey when his team discovered that astronomers had undercounted the number of galaxies in the observable universe by a factor of 10, revealing over 2 trillion individual galaxy systems, where previous estimates found only 200 billion. The discovery came from combining deep space images from the Hubble Space Telescope with sophisticated three-dimensional modeling techniques that could detect galaxies too faint to observe directly. When Consolis's team converted these images into three-dimensional maps showing galaxy distribution throughout cosmic history, they realized that over 90% of galaxies in the observable universe remain invisible to current telescopes. This cosmic census revision means that the observable universe contains at least 10 times more galaxies than stars in the Milky Way. If you could count one galaxy per second without stopping, it would take over 63,000 years to count them all. The total number of stars in these trillion galaxies exceeds the number of grains of sand on all beaches on Earth by a factor of 10,000. The undercounting occurred because distant galaxies appear much fainter than nearby ones, and many small galaxies that existed in the early universe have since merged together to form larger systems. When astronomers looked at distant regions of space, they could only detect the brightest, most massive galaxies. The numerous smaller, fainter galaxies remained below the detection threshold of even the most sensitive instruments. Think of it like trying to count all the lights in a distant city at night. You can easily see the bright street lights and neon signs, but millions of dim house lights, phone screens, and small bulbs remain invisible from far away. The bright lights you can count represent only a tiny fraction of the total illumination sources in the city. The team used mathematical models to infer the existence of these invisible galaxies based on how galaxy populations change over cosmic time. They discovered that the early universe contained many more small, faint galaxies than previously realized. As the universe aged, these small galaxies gradually merged together through gravitational interactions to form the larger galaxy systems we observe today. This merging process explains why nearby regions of space contain fewer total galaxies than distant regions, despite having the same amount of matter. The galaxies we see in our cosmic neighborhood represent the merged descendants of numerous smaller systems that existed billions of years ago. Looking at distant space allows us to see these ancestral galaxies before they combined. The James Webb Space Telescope has begun detecting some of these previously invisible galaxies, confirming predictions made by Consolis's statistical analysis. Webb's infrared sensors can observe the stretched light from small, distant galaxies that remained undetectable to previous generations of telescopes. Each newly discovered galaxy represents an entire stellar system, potentially containing billions of stars and planets. The revised galaxy count suggests that the universe contains far more potential sites for planet formation and biological evolution than previously estimated. If even a tiny fraction of these galaxies contain planets capable of supporting life, the number of potentially habitable worlds becomes astronomically large. The discovery also affects calculations about cosmic evolution and structure formation. 2 trillion galaxies worth of gravitational influence shapes how matter moves and accumulates on the largest scales. This additional gravitational pull affects the formation of cosmic filaments, galaxy clusters, and other large-scale structures throughout the universe. Furthermore, the abundance of galaxies provides important constraints on theories about dark matter and dark energy. The distribution and evolution of galaxy populations offers clues about how these mysterious components of the universe influence cosmic structure formation over billions of years. However, counting galaxies represents just one aspect of cosmic measurement. The techniques astronomers use to determine distances to these trillion galaxies reveal fundamental principles about how we can measure anything in a universe where perspective creates optical illusions on cosmic scales. Every measurement of cosmic distance relies on a geometric principle so simple that ancient Greek mathematicians used it to calculate the size of Earth, yet so precise that modern astronomers apply it to map galaxies billions of light years away. Parallax works by observing how nearby objects appear to shift position against distant backgrounds when viewed from different locations. Hold your finger at arm's length and look at it first with your left eye, then your right eye. Your finger appears to jump back and forth against the background wall. The closer your finger is to your face, the larger this apparent jump becomes. Astronomers use Earth's orbit around the Sun to create a massive parallax baseline by observing a star's position, waiting 6 months for Earth to move to the opposite side of its orbit, then measuring the star's position again. They can detect tiny shifts in stellar positions against the background of more distant stars. Earth's orbital diameter of 186 million miles provides a triangle baseline large enough to measure distances to nearby stars with extraordinary precision. The first successful stellar parallax measurement came in 1838 when Friedrich Bessel observed the star 61 Cygni. He detected a parallax angle of just 0.3 arcseconds, equivalent to the width of a dime viewed from a distance of 4 miles. This minuscule angle revealed that the star lay 11 light-years from Earth, proving that the universe contained vastly more empty space than anyone had imagined. Modern parallax measurements achieve precision, measured in micro-arcseconds. Angles so small they equal the width of a human hair seen from 100 miles away. The European Space Agency's Gaia mission has measured parallax distances to over 1 billion stars, with this incredible precision creating the most detailed three-dimensional map of our galactic neighborhood ever produced. Parallax forms the first rung of the cosmic distance ladder, a series of measurement techniques that build upon each other to reach ever greater distances. Each technique must be calibrated using the previous method before it can reliably measure farther objects. Parallax provides the foundation for all other distance measurements by establishing accurate distances to nearby stars. The limitation of parallax is that stellar shifts become too small to detect once stars lie more than a few thousand light-years from Earth. Even with space-based telescopes eliminating atmospheric distortion, current technology can only measure parallax angles down to about 10 micro-arcseconds. This corresponds to a maximum distance of roughly 10,000 light-years, covering less than 10% of the Milky Way's diameter. Beyond parallax range, astronomers must rely on standard candles, objects whose intrinsic brightness is known from physical principles or calibrated using nearby examples. Cepheid variable stars serve as excellent standard candles because their pulsation periods directly relate to their true luminosity. Once you know how bright a Cepheid should be and how bright it appears from Earth, the inverse square law of light reveals its distance. The cosmic distance ladder extends through multiple rungs: parallax for nearby stars, Cepheid variables for nearby galaxies, type Ia supernovae for distant galaxies, and redshift measurements for the most remote objects in the observable universe. Each step introduces additional uncertainty, but the overlapping ranges between methods allow astronomers to cross-check their measurements and identify systematic errors. Recent improvements in parallax precision have revealed errors in previous distance measurements that propagated through the entire cosmic distance ladder. When the Hipparcos mission revised distances to nearby Cepheid variables, it forced astronomers to recalibrate distances to distant galaxies and revise estimates of the universe's size and expansion rate. The Gaia mission continues refining parallax measurements with unprecedented accuracy, providing the most reliable foundation for cosmic distance measurements ever achieved. Each improvement in parallax precision ripples through the entire distance ladder, affecting our understanding of cosmic scale, galaxy evolution, and fundamental cosmological parameters. These precise geometric measurements become essential for understanding the next level of cosmic distance indicators: the pulsating stars that serve as cosmic lighthouses across intergalactic space. When a white dwarf star accumulates exactly 1.4 solar masses of material and explodes with the force of 5 billion suns, it creates a cosmic ruler more reliable than any human measurement standard ever devised. Type Ia supernovae represent the most powerful explosions in the modern universe, briefly outshining entire galaxies containing hundreds of billions of stars. These stellar detonations occur when a white dwarf star, the dense remnant of a sun-like star's death, pulls material from a nearby companion star until it reaches a critical mass threshold known as the Chandrasekhar limit. The explosion happens the same way every time because physics demands it. Once the white dwarf reaches 1.4 times the mass of our Sun, nuclear fusion ignites throughout the entire stellar remnant simultaneously. The star completely destroys itself in seconds, converting a significant fraction of its mass directly into energy, according to Einstein's famous equation relating mass and energy. This consistent explosion mechanism makes Type Ia supernovae perfect standard candles for cosmic distance measurement. Every Type Ia supernova reaches approximately the same peak brightness, equivalent to the luminosity of 5 billion suns. When astronomers observe these explosions in distant galaxies, they can calculate distances by comparing the supernova's apparent brightness to its known intrinsic luminosity. The technique works across enormous distances because Type Ia supernovae are so incredibly bright. They can be detected in galaxies over 10 billion light-years away, allowing astronomers to measure distances across roughly 70% of the observable universe's radius. No other standard candle technique can reliably reach such extreme distances. Saul Perlmutter, Brian Schmidt, and Adam Rees used Type Ia supernovae in the 1990s to make one of the most shocking discoveries in modern cosmology. Their teams expected to find that cosmic expansion was gradually slowing down due to gravitational attraction between distant galaxies. Instead, they discovered that expansion is accelerating, driven by a mysterious force now called dark energy. This discovery earned the researchers the Nobel Prize in Physics and revolutionized our understanding of cosmic evolution. Dark energy appears to comprise roughly 68% of the universe's total energy content, yet its nature remains completely unknown. The existence of dark energy was revealed entirely through precise measurements of Type Ia supernova distances and redshifts. Recent supernova surveys have observed thousands of these stellar explosions across cosmic history, creating detailed maps of how cosmic expansion has changed over billions of years. The data reveals that dark energy's influence has grown stronger as the universe aged, while matter's gravitational influence has weakened due to decreasing density as space expands. Type Ia supernovae also provide crucial calibration points for other distance measurement techniques. By observing these explosions in galaxies that also contain Cepheid variable stars, astronomers can cross-check and refine the cosmic distance ladder. This calibration process has revealed systematic errors in previous distance measurements and improved the precision of cosmic scale determinations. The James Webb Space Telescope has begun observing Type Ia supernovae at unprecedented distances, detecting explosions from when the universe was less than half its current age. These observations provide new data points for understanding how cosmic expansion has evolved throughout universal history and help constrain theories about dark energy's properties. However, recent supernova observations have revealed subtle variations in explosion properties that complicate their use as perfect standard candles. Some Type Ia supernovae appear slightly brighter or dimmer than average, requiring correction factors based on their host galaxy properties and explosion characteristics. These refinements continue improving the precision of supernova distance measurements. The discovery that stellar explosions could serve as cosmic rulers opened the door to understanding an even more fundamental class of stellar timepieces: the pulsating variables that beat with rhythms spanning millions of years. Delta Cephei pulses with the mechanical precision of a cosmic metronome, brightening and dimming every 5 days, 12 hours, and 9 minutes, in a rhythm that has remained unchanged for millions of years. This star, located 700 light-years away in the constellation Cepheus, represents one of the most important classes of objects in cosmic distance measurement. Cepheid variable stars expand and contract. Like beating hearts, their surfaces moving in and out by millions of miles as internal pressure waves ripple through their stellar atmospheres. The pulsation mechanism works because these massive stars exist in a state of delicate instability. As nuclear fusion in their cores produces energy, radiation pressure pushes outward against gravitational collapse. When the star contracts slightly, it heats up and becomes more opaque to its own light. This trapped energy causes rapid expansion, which cools the star and makes it more transparent, allowing energy to escape and causing contraction to begin again. This stellar breathing creates a perfect relationship between pulsation period and intrinsic brightness. More massive, luminous Cepheids pulsate more slowly than smaller, dimmer ones. A Cepheid that pulses every 10 days is roughly 10 times brighter than one that pulses every day. This period luminosity relationship provides a cosmic measuring stick that works across intergalactic distances. Henrietta Swan Leavitt discovered this relationship in 1912 while studying Cepheids in the Small Magellanic Cloud. She realized that once astronomers could determine the true brightness of Cepheids at a known distance, they could use the period luminosity law to measure distances to any galaxy containing these pulsating stars. Modern Cepheid observations can determine distances accurate to within 5% across millions of light-years. The Hubble Space Telescope has observed Cepheids in galaxies up to 100 million light-years away, providing crucial calibration for more distant measurement techniques. Each observation requires weeks of monitoring to measure the star's pulsation period and average brightness. The technique faces challenges at extreme distances where individual Cepheids become too faint to observe clearly. Advanced telescopes must separate the light from a single pulsating star from the combined glow of billions of other stars in the same galaxy. This requires exceptional image resolution and careful analysis to avoid contamination from nearby stellar sources. Recent discoveries have revealed that Cepheid properties depend on the chemical composition of their host galaxies. Stars in metal-rich galaxies pulse slightly differently than those in metal-poor systems, requiring corrections to distance measurements based on galactic chemical evolution. These refinements have improved the accuracy of the cosmic distance ladder and reduced systematic uncertainties. The James Webb Space Telescope can observe Cepheids at greater distances than ever before, extending this measurement technique deeper into the universe. Webb's infrared sensitivity reduces the effects of dust obscuration that can dim Cepheid light and bias distance measurements. This capability allows more precise calibration of secondary distance indicators used for cosmological measurements. Cepheid observations have also revealed unexpected features of galactic structure and evolution. The distribution of these young massive stars traces recent star formation activity and reveals the spiral arm patterns of distant galaxies. Their chemical compositions provide insights into how galaxies have enriched their interstellar medium with heavy elements over billions of years. Long-term monitoring programs have tracked individual Cepheids for decades, revealing subtle changes in their pulsation periods that reflect stellar evolution processes. Some Cepheids show period changes of seconds per year as they evolve through different phases of post-main sequence stellar development. These pulsating stellar chronometers have provided the foundation for one of the most puzzling discoveries in modern cosmology: the realization that different methods of measuring cosmic expansion produce conflicting results that challenge our understanding of fundamental physics. The cosmic microwave background radiation carries a message from the universe's infancy that contradicts everything we measure about how fast space expands today, creating a crisis that threatens to overturn modern cosmology. This ancient light comes from the moment, roughly 380,000 years after the Big Bang, when the universe first became transparent to electromagnetic radiation. Before this epoch, the cosmos was so hot and dense that photons could not travel freely through space. When the universe finally cooled enough for atoms to form, light could suddenly stream freely across vast distances. That primordial light has been traveling through expanding space for over 13 billion years, carrying information about conditions in the early universe encoded in tiny temperature variations across the sky. The Planck satellite mapped these fluctuations with extraordinary precision, revealing patterns that allow astronomers to calculate cosmic parameters with unprecedented accuracy. According to measurements of the cosmic microwave background, the universe should be expanding at a rate of 67.4 kilometers per second per megaparsec of distance. This means that two galaxies separated by 3.3 million light-years should be moving apart at 67.4 kilometers per second due to cosmic expansion alone. However, direct measurements of the current expansion rate using nearby galaxies for discovering that cosmic expansion is accelerating has led efforts to improve the precision of local expansion measurements using the Hubble Space Telescope and James Webb Space Telescope. Recent observations with James Webb have confirmed the Hubble measurements with even greater precision, ruling out many potential sources of systematic error. The tension appears to be real, not the result of measurement problems or contamination from intervening cosmic structures. One possible explanation is that dark energy, the mysterious force driving cosmic acceleration, has changed its properties over time. If dark energy was weaker in the past and has grown stronger recently, it could explain why early universe predictions differ from current measurements. However, the standard model of cosmology assumes that dark energy's properties remain constant throughout cosmic history. Alternative theories propose modifications to general relativity that could affect cosmic expansion on large scales. These modified gravity theories suggest that Einstein's equations might require corrections when applied to the entire universe, similar to how quantum mechanics required modifications to classical physics at atomic scales. Another possibility is the existence of additional forms of dark matter or energy that have not yet been discovered. Early dark energy, sterile neutrinos, or exotic particles could have influenced cosmic evolution in ways that create the observed discrepancy between early and late measurements. The tension has grown more significant as measurement precision has improved. Early estimates of the expansion rate were uncertain by 20% or more, making the current 6% discrepancy invisible. As systematic errors have been reduced and more data has been collected, the disagreement has become statistically compelling. Some researchers suggest that we might live in an unusual region of the universe where expansion proceeds differently than the cosmic average. Local gravitational anomalies, or large-scale structure, could create the appearance of faster expansion without requiring modifications to fundamental physics. The resolution of the Hubble tension may require revolutionary changes to our understanding of cosmic evolution, dark energy, or the nature of space and time itself. This measurement crisis reveals that even our most precise cosmic observations still leave fundamental questions about the universe's behavior unanswered. However, these expansion measurements depend on understanding the invisible framework that holds galaxies in place across the vast cosmic web, spanning billions of light-years. 27% of the universe consists of a form of matter that refuses to emit, absorb, or reflect light. Yet without it, galaxies would fly apart, and cosmic structure would never have formed in the first place. Dark matter reveals its presence only through gravitational effects on visible matter and light. Galaxies rotate too fast to hold together based on the gravity from their visible stars alone. galaxy clusters move in ways that require 5 times more mass than astronomers can observe directly. Gravitational lensing bends light around massive objects in patterns that demand invisible mass concentrations. The evidence for dark matter comes from multiple independent observations that all point to the same conclusion. Vera Rubin's measurements of galaxy rotation curves in the 1970s showed that stars in galactic outskirts orbit much faster than expected if only visible matter provided gravitational force. According to Newton's laws, these outer stars should either slow down or fly away into intergalactic space. Computer simulations of cosmic structure formation cannot reproduce the large-scale distribution of galaxies without including dark matter as the dominant gravitational influence. When astronomers model the universe using only ordinary matter, galaxies fail to form in the observed locations, and cosmic filaments never develop the structure we observe today. The cosmic web of dark matter forms an invisible skeleton upon which visible matter accumulates. Dark matter particles, whatever they are, interact only through gravitational force and possibly the weak nuclear force. They do not collide with each other or with ordinary matter except through gravity, allowing them to form smooth, extended halos around galaxies. These dark matter halos extend far beyond the visible boundaries of galaxies, creating gravitational wells that trap ordinary matter and facilitate star formation. The Milky Way sits within a dark matter halo roughly 600,000 light-years in diameter, containing approximately 1 trillion solar masses of invisible matter. Galaxy collisions reveal dark matter's properties through gravitational lensing effects. When galaxy clusters collide, their dark matter components pass through each other almost unaffected, while ordinary matter interacts electromagnetically and gets stripped away. The famous bullet cluster collision shows clear separation between visible matter and gravitational lensing effects, providing direct evidence for dark matter's existence. Current theories propose several candidates for dark matter particles. Weakly interacting massive particles, or WIMPs, represent the leading theoretical possibility. These hypothetical particles would have masses similar to atomic nuclei, but interact only through gravity and the weak nuclear force. Despite decades of searching with increasingly sensitive detectors, no WIMP particles have been directly observed. Alternative candidates include axions, extremely light particles that could be produced in enormous numbers throughout the universe. Sterile neutrinos, primordial black holes, and exotic particles predicted by supersymmetry theories also remain possibilities for explaining dark matter's properties. The distribution of dark matter affects cosmic structure formation on all scales. Small-scale density fluctuations in dark matter during the early universe grew through gravitational attraction to form the first stellar nurseries. Without dark matter's gravitational scaffolding, the universe would contain only a smooth distribution of hydrogen and helium gas, with no galaxies, stars, or planets. Dark matter also influences cosmic expansion through its gravitational effects. Although dark energy drives accelerating expansion, dark matter provides gravitational resistance that slows the acceleration rate. The balance between dark matter's attractive gravity and dark energy's repulsive effect determines how cosmic expansion will evolve over trillions of years. Recent observations with the James Webb Space Telescope have revealed that massive galaxies formed earlier in cosmic history than theoretical models predict. This suggests that dark matter halos assembled more rapidly than current simulations indicate, requiring refinements to our understanding of how dark matter behaves during structure formation. The invisible cosmic web created by dark matter extends throughout the observable universe, connecting galaxy clusters across billions of light-years through tenuous filaments of gravitating matter. These connections influence galaxy evolution by channeling gas flows and determining how galaxies acquire material for continued star formation. Yet, even this vast network of invisible matter pales in comparison to the cosmic voids that separate these dark matter structures. Regions of space so empty, they challenge our understanding of how matter can be distributed on the largest scales. The Boötes void stretches 330 million light-years across and contains almost nothing. Yet this cosmic desert holds the key to understanding why galaxies exist anywhere at all. This enormous region of nearly empty space is so vast that if the Milky Way sat at its center, the nearest major galaxy would be invisible to the naked eye. The void contains only a handful of small galaxies scattered throughout a volume that should hold thousands of massive stellar systems. It represents one of the largest supervoids ever discovered, earning the nickname the Great Nothing. Cosmic voids make up roughly 80% of the universe's volume, but contain less than 5% of its matter. These regions are not completely empty. They contain dark matter, trace amounts of gas, and occasional isolated galaxies, but their density is less than 1/10 the cosmic average. If the average universe has the density of air, cosmic voids have the density of the space between air molecules. The existence of such enormous empty regions reveals fundamental information about how cosmic structure formed after the Big Bang. In the early universe, matter was distributed almost uniformly throughout space, with only tiny density fluctuations of about 1 part in 100,000. Gravity amplified these microscopic variations over billions of years, pulling matter out of some regions and into others. Areas that started slightly denser than average attracted more matter through gravitational pull, eventually becoming the galaxy clusters and filaments we observe today. Regions that began slightly less dense lost material to their neighbors, growing increasingly empty over cosmic time. The largest voids represent areas that started with the lowest initial density and have been losing matter for over 13 billion years. This cosmic sorting process creates the observed web-like structure of the universe, with matter concentrated into thin filaments and sheets separated by vast voids. The pattern resembles soap foam or Swiss cheese, with dense walls surrounding empty bubbles. Galaxy superclusters trace the dense regions, while supervoids occupy the spaces between them. Voids play a crucial role in galaxy evolution by providing low-density environments where galaxies can evolve in relative isolation. Galaxies within voids experience fewer gravitational disturbances and galactic collisions than those in dense clusters. This allows void galaxies to retain more of their original gas content and continue forming stars at steady rates over billions of years. The expansion of cosmic voids also provides important tests of general relativity and alternative theories of gravity. Einstein's equations predict how matter should flow out of these regions under gravitational influence. Modified gravity theories propose different behaviors that could potentially be detected through precise measurements of void expansion rates. Recent surveys have discovered that voids are not completely spherical or randomly distributed. They show preferred orientations and appear connected through channels of even lower density. This cosmic architecture provides clues about conditions during the inflationary epoch immediately after the Big Bang, when quantum fluctuations were amplified to create the initial density pattern. The James Webb Space Telescope can now observe galaxies within distant voids, providing new insights into how these isolated systems evolve differently from galaxies in dense environments. Webb's observations reveal that void galaxies often have unusual properties, including higher rates of star formation and different chemical compositions than their counterparts in denser regions. Cosmic voids also affect the propagation of light from distant sources, creating subtle lensing effects that influence astronomical observations. Photons traveling through these underdense regions experience slightly different gravitational effects than light passing through average density space, creating systematic effects that must be accounted for in precise cosmological measurements. These vast, empty regions demonstrate that the universe's most important features might be defined not by what they contain, but by what they lack, setting the stage for discoveries about ancient galaxies that challenge everything we thought we knew about cosmic evolution. JDES GSZ140 blazes across space like a cosmic impossibility, shining with the light of hundreds of millions of stars from an epoch when the universe was barely old enough to create its first stellar nurseries. This galaxy appears to us as it existed just 290 million years after the Big Bang, when the universe was only 2% of its current age. At that early cosmic moment, the universe should have contained mostly hydrogen and helium gas, with perhaps a few small collections of the first primitive stars. Instead, James Webb Telescope images reveal a fully formed galaxy system that appears surprisingly large, bright, and well organized. The discovery violates theoretical predictions about how quickly galaxies can assemble. Computer simulations suggest that building a galaxy this massive requires hundreds of millions of years of gradual matter accumulation through gravitational attraction. Stars must form, live out their lives, explode as supernovae, and enrich the surrounding gas with heavy elements before second-generation stellar systems can develop the complexity observed in JDES GS-Z140. Think of it like discovering a modern skyscraper in an archaeological dig from the Stone Age. The materials, tools, and organizational complexity required to build such a structure simply should not have existed at that point in history. Yet, there it stands, demanding an explanation for how such rapid development occurred. The galaxy's spectrum reveals another shocking feature. It contains significant amounts of carbon, oxygen, and other heavy elements that can only be produced inside stellar cores through nuclear fusion. These elements require multiple generations of massive stars to live, die, and scatter their processed materials through space before accumulating in sufficient quantities to form new stellar systems. Even more puzzling, JDES GS-Z140 shows active star formation occurring at rates much higher than expected for such early cosmic times. The galaxy appears to be converting gas into new stars at a pace that should have exhausted its fuel supply within a few 100 million years. This suggests either that early galaxies had access to much larger gas reservoirs than current models predict, or that star formation processes operated more efficiently in the primordial universe. The galaxy's brightness indicates it contains billions of stars packed into a relatively compact region. This stellar density implies that galaxy mergers and interactions were already shaping cosmic structure formation within the first few 100 million years after the Big Bang. Such early merger activity requires that numerous smaller proto-galactic systems had already formed and begun gravitationally interacting. Recent discoveries have revealed dozens of similar early galaxies that challenge conventional timelines of cosmic evolution. Each observation pushes back the epoch when complex galactic systems first appeared, suggesting that the early universe was a much more active and rapidly evolving environment than previously understood. The existence of these impossible galaxies has forced astronomers to reconsider fundamental assumptions about cosmic inflation, dark matter behavior, and star formation efficiency in primordial environments. Some theories propose that dark matter formed more concentrated structures earlier than standard models predict, providing deeper gravitational wells for rapid galaxy assembly. Alternative explanations suggest that the first stars were much more massive than typical modern stars, burning through their nuclear fuel more rapidly and producing heavy elements at accelerated rates. These theoretical population 3 stars could have seeded the early universe with processed materials much faster than current stellar evolution models indicate. The James Webb Telescope continues discovering galaxies from even earlier cosmic epochs, each observation revealing that complex structure formation began almost immediately after the universe became transparent to light. These findings suggest that the transition from cosmic dark ages to the epoch of galaxy formation occurred more rapidly and dramatically than anyone expected. However, these ancient galactic systems pale in comparison to recent discoveries about the fundamental limits that govern how quickly any cosmic structure can possibly grow. Alan Guth was trying to solve a completely different problem in 1980 when he accidentally discovered that the universe underwent a period of expansion so rapid it nearly violated the laws of physics themselves. The mystery Guth was investigating involved the flatness and uniformity of space on cosmic scales. Observations showed that the universe appears remarkably smooth and geometrically flat across vast distances, yet the Big Bang model predicted that space should be curved and filled with chaotic irregularities left over from the violent creation event. Guth realized that if the universe expanded exponentially during its first fraction of a second, this cosmic inflation could smooth out initial irregularities and flatten space geometry through sheer stretching. During inflation, space expanded faster than light could travel, growing from smaller than a proton to larger than a grapefruit in less time than it takes light to cross an atomic nucleus. This expansion rate represents the ultimate speed limit for cosmic growth. During inflation, the scale factor of the universe doubled every 10 to the power of negative 37 seconds. To put this in perspective, if inflation lasted for just 1 second at this rate, a region the size of a proton would grow larger than the currently observable universe. The inflationary epoch solved several major cosmological puzzles simultaneously. It explained why space appears flat rather than curved, why the cosmic microwave background radiation has nearly uniform temperature, and why we do not observe exotic relics like magnetic monopoles that should have been produced during the Big Bang. However, inflation also created new mysteries about cosmic structure formation. If space expanded so rapidly that it smoothed out all irregularities, how did galaxies and galaxy clusters ever form? The answer lies in quantum mechanical fluctuations that occurred during the inflationary period itself. Even during the most rapid expansion phase, quantum uncertainty principles created tiny density variations in the fabric of space. These microscopic fluctuations were stretched to enormous scales by inflation, becoming the seeds from which all cosmic structure eventually grew. Galaxy clusters, superclusters, and cosmic voids all trace back to quantum events that occurred when the universe was smaller than an atom. Modern observations of the cosmic microwave background radiation reveal the imprint of these primordial quantum fluctuations as tiny temperature variations across the sky. The pattern matches theoretical predictions for inflation with extraordinary precision, providing strong evidence that this period of ultra-rapid expansion actually occurred. The discovery of cosmic inflation also revealed fundamental limits on how quickly any physical process can operate. Even during the most extreme conditions imaginable, cosmic expansion could not exceed certain theoretical boundaries imposed by quantum mechanics and general relativity. These limits suggest that there are absolute constraints on how rapidly any cosmic structure can form or evolve. Recent measurements using gravitational wave detectors have begun searching for signatures of cosmic inflation in the polarization patterns of ancient light. If inflation occurred as theorized, it should have produced gravitational waves that left detectable imprints on the cosmic microwave background. Finding these signatures would provide direct evidence for the inflationary epoch and reveal details about conditions during the universe's first moments. The James Webb Space Telescope observations of early galaxies provide additional tests of inflationary theory. If inflation correctly describes cosmic history, then the distribution and properties of the first galactic systems should match predictions based on the quantum fluctuations that were amplified during the inflationary period. Some alternative theories propose that the universe underwent multiple periods of inflation, or that inflation proceeded at variable rates during different epochs. These modified scenarios could explain why early galaxies appear to have formed more rapidly than standard models predict. The speed limit discovered through inflation research applies not just to cosmic expansion, but to all physical processes operating under extreme conditions. Understanding these fundamental boundaries has become crucial for interpreting observations of the largest cosmic structures that span impossible distances. If you could travel at the speed of light across the Hercules Corona Borealis Great Wall, the journey would take 10 billion years, longer than twice the age of our solar system. This cosmic megastructure represents the largest known formation in the observable universe, spanning roughly 10 billion light-years from end to end. The structure consists of galaxy clusters, superclusters, and connecting filaments arranged in a wall-like pattern that stretches across approximately 10% of the observable universe's diameter. The discovery came from mapping gamma-ray bursts, the most powerful explosions known to occur in the modern universe. These cosmic detonations shine briefly with the luminosity of a billion suns, making them visible across enormous distances. When astronomers plotted the locations of thousands of gamma-ray bursts in three-dimensional space, they discovered that these events were not randomly distributed but clustered along massive cosmic structures. The Great Walls exist after the Big Bang. Gravity working at the speed of light could not have organized material across 10 billion light-years within the universe's 13.8 billion year history. The structure is simply too large to have formed through conventional gravitational collapse. The Great Wall's scale becomes even more mind-boggling when compared to human experience. If you could shrink the entire observable universe down to the size of Earth, this cosmic structure would stretch from the North Pole to the South Pole and back again. It contains the mass of hundreds of thousands of galaxy clusters, each cluster containing thousands of individual galaxies. Recent computer simulations struggle to reproduce structures this large using standard models of cosmic evolution. The simulations can create galaxy filaments and walls spanning hundreds of millions of light-years. But formations approaching 10 billion light-years in extent remain extremely rare in theoretical models. This suggests that either our understanding of early cosmic conditions is incomplete, or that additional physical processes influence structure formation. One possible explanation involves modifications to our understanding of dark matter behavior during the early universe. If dark matter interacted more strongly with itself or with ordinary matter during the first billion years after the Big Bang, it could have facilitated more rapid structure formation than current models predict. Alternative theories propose that cosmic inflation created larger initial density fluctuations than previously thought. If the primordial seeds of structure formation were already quite large when inflation ended, they could have grown into these enormous formations more easily through subsequent gravitational evolution. The discovery of the Great Wall also affects calculations about the total amount of matter in the observable universe. Structures this massive contain enormous quantities of dark matter and ordinary matter that must be accounted for in cosmic inventory calculations. The gravitational influence of such formations affects the motion of surrounding galaxies across distances spanning billions of light-years. Observations with next-generation telescopes may reveal even larger structures hiding in the depths of space. The James Webb Space Telescope and upcoming extremely large telescopes could detect the most distant galaxy clusters and filaments, potentially mapping cosmic architecture across even greater volumes of space. The existence of walls spanning 10 billion light-years demonstrates that cosmic structure extends to the largest scales we can observe, raising profound questions about what lies beyond the edge of our observational horizon. However, these vast cosmic structures create a paradox when we consider the relationship between distance and time in an expanding universe. When astronomers observe the galaxy Maxone 1149 Jadone, located 13.2 billion light-years away, they are seeing light that began its journey toward Earth when the universe was only 500 million years old. This fundamental aspect of cosmic observation means that every astronomical measurement is actually an archaeological expedition into the universe's past. The farther we look into space, the further back in time we see, because light travels at a finite speed and takes time to cross cosmic distances. Light from the sun takes 8 minutes to reach Earth, so we always see our star as it was 8 minutes ago. Light from the nearest star beyond the sun, Proxima Centauri, takes 4 years to reach us. When we observe this star, we see it as it existed 4 years in the past. For all practical purposes, Proxima Centauri could have exploded 2 years ago, and we would not know until 2 years from now. This light travel time effect becomes increasingly dramatic at cosmic distances. The Andromeda galaxy appears to us as it was 2.5 million years ago, when early human ancestors were beginning to use stone tools. The light now reaching us from Andromeda began its journey before Homo sapiens existed as a species. Distant galaxy clusters show us cosmic structure as it appeared billions of years ago, when the universe was much younger and denser than today. The most distant observable galaxies reveal conditions from the universe's infancy, when the first stellar systems were just beginning to form from primordial hydrogen and helium gas. This temporal archaeology allows astronomers to study cosmic evolution directly by observing how galaxies, stars, and large-scale structures appeared at different epochs in universal history. By comparing nearby galaxies to distant ones, researchers can trace how cosmic systems have changed and evolved over billions of years. The James Webb Space Telescope exploits this time travel effect to study galaxy formation during the universe's first billion years. Each observation captures ancient light that preserves information about conditions, processes, and physical laws operating in cosmic environments completely different from the modern universe. However, the expanding universe complicates this relationship between distance and look-back time. Space itself has been growing during the light travel time, carrying distant galaxies even farther away by the time their light reaches our telescopes. A galaxy that was 30 billion light-years away when it emitted the light we observe today is now over 40 billion light-years distant. This expansion effect means that the most distant observable objects are not located at distances equal to their light travel times. The cosmic microwave background radiation has been traveling toward us for over 13 billion years, but the regions that emitted this radiation are now roughly 46 billion light-years away due to cosmic expansion during the light travel time. The relationship between distance and look-back time also varies depending on cosmic expansion history. During periods when expansion was slowing down, light could cover greater distances in a given time interval. During epochs of accelerating expansion, light made less distance progress relative to the expanding space through which it traveled. These temporal effects create observational selection biases that astronomers must account for when interpreting cosmic surveys. Distant objects appear as they were in younger, more active phases of cosmic evolution, while nearby objects show us mature, evolved systems. Comparing these populations requires careful corrections for evolutionary effects and cosmic expansion. The finite speed of light also creates a fundamental limit on cosmic communication. If we detected a signal from a civilization in the Andromeda galaxy tomorrow, any reply we sent would not reach them for another 2.5 million years. By the time our message arrived, their entire civilization could have evolved beyond recognition or become extinct. This light travel time archaeology has revealed one of the most shocking discoveries in observational cosmology, the moment when multiple independent measurement techniques suddenly agreed on something that seemed impossible. In 1998, 2 independent research teams studying distant supernovae reached the same impossible conclusion. The universe's expansion is accelerating, driven by a mysterious force that comprises nearly 70% of all existence. The High-Z Supernova Search Team, led by Brian Schmidt and the Supernova Cosmology Project, directed by Saul Perlmutter, had been conducting competing surveys to measure how cosmic expansion was slowing down over time. Both teams expected to find that gravitational attraction between galaxies was gradually decelerating the expansion rate, just as Earth's gravity slows down a thrown baseball. Instead, their independent analyses of Type Ia supernova observations revealed that distant galaxies were moving away from us faster than expected based on their distances. The expansion rate was not slowing down, it was speeding up. The universe was accelerating like a car with the gas pedal pressed to the floor. This discovery contradicted every theoretical prediction about cosmic evolution. Gravity is an attractive force that should pull objects together, not push them apart. The standard model of particle physics contained no known mechanism that could drive accelerating cosmic expansion on such enormous scales. The two teams initially suspected systematic errors in their measurements. They checked their supernova distance calculations, verified their redshift measurements, and searched for any observational biases that could create false signals of acceleration. Independent analysis by multiple research groups confirmed the same startling result. Cosmic expansion was indeed speeding up. The discovery required the existence of a previously unknown component of the universe with exotic properties. This dark energy, as it came to be called, must exert negative pressure that overcomes gravitational attraction on cosmic scales. Unlike ordinary matter and energy, dark energy becomes more dominant as the universe expands and density decreases. Current observations suggest that dark energy comprises roughly 68% of the universe's total energy content. Dark matter accounts for another 27%, leaving ordinary matter, everything made of atoms, including stars, planets, and living beings, as less than 5% of cosmic inventory. The nature of dark energy remains completely mysterious despite decades of intensive research. Leading theories propose that it represents the energy density of empty space itself, arising from quantum mechanical fluctuations in the vacuum. However, theoretical calculations of vacuum energy density exceed observational limits by a factor of 10 to the power of 120, making this the worst prediction in the history of physics. Alternative explanations include modifications to Einstein's general relativity that could create apparent acceleration without requiring exotic energy components. These modified gravity theories propose that gravitational attraction weakens on cosmic scales in ways that Einstein's equations do not capture. The discovery of cosmic acceleration earned the Nobel Prize in Physics in 2011 and fundamentally changed our understanding of cosmic fate. Instead of eventually collapsing back on itself in a big crunch, the universe will continue expanding forever, with galaxies becoming increasingly isolated as space stretches between them. Recent observations with the James Webb Space Telescope have confirmed the existence of dark energy by observing its effects during earlier epochs of cosmic history. The telescope can detect supernovae from when the universe was less than half its current age, providing data points for measuring how dark energy's influence has evolved over billions of years. The concordance between multiple independent measurement techniques, supernovae, cosmic microwave background observations, galaxy clustering surveys, and gravitational lensing studies all point to the same cosmological model dominated by dark energy and dark matter. This convergence of evidence from completely different physical phenomena provides strong support for our current understanding of cosmic composition. However, the discovery of dark energy has opened more questions than it answered, particularly about what ancient cosmic radiation reveals about the universe's ultimate size and structure. The faint glow of ancient light that fills every cubic inch of space carries encoded messages about regions of the universe so distant that we will never see them directly, no matter how advanced our telescopes become. This cosmic microwave background radiation represents the afterglow of the Big Bang itself, emitted when the universe was just 380,000 years old and 1,000 times smaller than it is today. Before this moment, space was so hot and dense that atoms could not form, making the universe opaque to electromagnetic radiation like the inside of a star. When the cosmos finally cooled enough for electrons and protons to combine into hydrogen atoms, light could suddenly stream freely across vast distances. This recombination event created a flash of radiation that filled the entire universe, and we still observe the stretched remnants of this primordial light as microwave radiation coming from all directions in space. The temperature variations in this ancient light appear tiny, just a few hundred thousandths of a degree difference across the sky, but they encode vast amounts of information about cosmic structure and evolution. These fluctuations represent the imprint of sound waves that propagated through the dense plasma of the early universe before atoms formed. Detailed analysis of the cosmic microwave background's temperature pattern reveals the universe's geometry, composition, and expansion history with extraordinary precision. The data indicates that space is geometrically flat to within measurement error, containing roughly 68% dark energy, 27% dark matter, and 5% ordinary matter. More importantly, for understanding cosmic size, the microwave background places fundamental constraints on the universe's total extent beyond what we can observe directly. The statistical properties of temperature fluctuations depend on the universe's curvature and total size in ways that can be measured, even if the actual boundaries lie beyond our observational horizon. If the universe were finite and smaller than the observable region, we would see repeated patterns in the microwave background as light wrapped around cosmic boundaries. The absence of such repetitions indicates that the universe extends far beyond what we can directly observe, possibly by factors of hundreds or thousands. Recent analyses suggest the universe is at least 250 times larger than the observable portion based on constraints from the cosmic microwave background. This implies a minimum total diameter of over 20 trillion light-years for the entire cosmos, making the observable universe a tiny bubble within an incomprehensibly vast reality. The microwave background also reveals information about cosmic topology, the overall shape and connectivity of space itself. Different topological models predict specific patterns of correlations in the ancient light that can potentially distinguish between infinite universes and finite ones with exotic geometries. Some theoretical models propose that space has a complex topology similar to a three-dimensional version of a donut or pretzel, where traveling far enough in one direction eventually brings you back to your starting point. The cosmic microwave background provides the most sensitive test for such exotic spatial geometries. Precision measurements by the Planck satellite have mapped temperature variations in the ancient light with unprecedented detail, revealing subtle features that constrain models of cosmic inflation and early universe physics. The data supports scenarios where inflation created a universe much larger than the observable region we inhabit. The polarization patterns in cosmic microwave background radiation carry additional information about conditions during the universe's first moments. These patterns could potentially reveal signatures of gravitational waves produced during cosmic inflation, providing direct evidence for the rapid expansion phase that established the universe's large-scale structure. Future ground-based and space-based missions will measure the microwave background with even greater precision, potentially detecting primordial gravitational wave signatures or other exotic signals from the universe's birth. These observations could reveal whether the cosmos is finite or infinite, and provide insights into the fundamental nature of space and time. The ancient light that surrounds us thus serves as a cosmic messenger, carrying information about regions of reality that lie forever beyond direct observation, but influence the structure and evolution of everything we can see. These revelations about cosmic architecture pale in comparison to recent discoveries about gravitational monsters so massive they challenge our understanding of what can possibly exist. At the heart of the galaxy, TON 618, lurks a black hole containing the mass of 66 billion suns, an object so massive that its event horizon could swallow our entire solar system with room for thousands more. This ultramassive black hole challenges everything astronomers thought they knew about how such objects can grow. Black holes form when massive stars collapse, creating stellar remnants typically containing only a few times the sun's mass. Growing from stellar mass to billions of solar masses should require hundreds of millions of years of continuous feeding, yet TON 618's monster black hole exists in the early universe when such growth times were not available. The black hole's event horizon, the point of no return beyond which nothing can escape, spans roughly 800 billion miles across. Light would take nearly 5 days to travel from one side to the other. If this black hole replaced our Sun, its event horizon would extend beyond the orbit of Pluto, engulfing all 8 planets and the entire asteroid belt. Recent discoveries with the James Webb Space Telescope have revealed even more puzzling examples of early supermassive black holes. Some galaxies observed when the universe was less than 1 billion years old already contain black holes with masses exceeding 1 billion suns. These objects appear to have grown impossibly quickly in the cosmic timescales available. The problem becomes clear when considering black hole feeding mechanisms. Even under ideal conditions, black holes can only consume matter at a maximum rate determined by the radiation pressure from their accretion disks. This Eddington limit sets an upper bound on how rapidly black holes can grow, and even at this maximum rate, reaching billion solar mass scales requires hundreds of millions of years. One possible solution involves primordial black holes that form directly from density fluctuations in the early universe rather than stellar collapse. These theoretical objects could have started with much larger initial masses, giving them a head start on growth that could explain the observed population of early supermassive black holes. Alternative theories propose that the first generation of stars, formed from pure hydrogen and helium, were much more massive than any stars that exist today. These population 3 stars could have reached masses of hundreds or thousands of suns before collapsing into correspondingly massive black holes that served as seeds for rapid growth. The gravitational influence of supermassive black holes extends far beyond their event horizons, affecting galaxy evolution across distances of hundreds of thousands of light years. These cosmic monsters regulate star formation in their host galaxies by heating surrounding gas through energetic jets and radiation from their accretion disks. Black hole mergers detected by gravitational wave observatories reveal that these objects can combine to create even more massive systems. When 2 galaxies containing supermassive black holes merge, their central black holes eventually spiral together and coalesce, releasing enormous amounts of energy in the form of gravitational waves that ripple through space-time itself. The most massive black holes also serve as cosmic laboratories for testing general relativity under extreme conditions. Near the event horizon, gravitational fields become so strong that space and time are severely warped, creating effects that have no analogy in human experience. Matter falling into these objects experiences spaghettification, stretching into thin streams as tidal forces overcome molecular bonds. Recent observations have begun resolving the immediate environments around supermassive black holes, revealing the complex dynamics of matter spiraling toward these cosmic drain holes. The Event Horizon Telescope captured the first direct image of a black hole shadow in the galaxy METI 7, showing the dark silhouette surrounded by glowing material heated to billions of degrees. These ultramassive objects also affect cosmic evolution on the largest scales. Their formation and growth are intimately connected to galaxy formation and the development of large-scale structure throughout the universe. Understanding how such massive black holes can exist pushes the boundaries of our comprehension about what the universe allows to form. Yet, even these gravitational monsters occupy only tiny regions compared to the possibility that the universe itself might be infinite in extent. making our observable portion an infinitesimal fraction of total reality. If you could travel to the edge of the observable universe and look outward, you would see another 46 billion light-year sphere of galaxies, stars, and cosmic structures extending in all directions, with no end in sight. The observable universe represents only the region from which light has had time to reach us since the Big Bang began 13.8 billion years ago. This creates a spherical boundary centered on Earth, not because we occupy a special location, but simply because we are the observers. Every point in the universe sits at the center of its own observable sphere. Current observations cannot determine whether space extends infinitely beyond our observational horizon, or eventually comes to an end at some unimaginably distant boundary. The cosmic microwave background radiation and other cosmological measurements are consistent with both finite and infinite universe models, leaving this fundamental question about reality's ultimate extent unresolved. If the universe is infinite, then it contains an infinite number of galaxies, stars, and planets, arranged in patterns that repeat on scales far larger, must occur somewhere, and indeed must occur infinitely many times. Alternative models propose that the universe is finite but has no boundary, similar to the surface of a sphere where you can travel in any direction forever without reaching an edge, yet the total area remains finite. In such models, space curves back on itself in dimensions we cannot directly perceive, creating a closed cosmos with finite volume but no borders. Some theories suggest that our observable universe represents just one bubble in an eternal inflation process that creates infinitely many separate cosmic regions. Each bubble would have its own physical laws, particle types, and fundamental constants, making our observable universe one member of an infinite multiverse of possible realities. The question of cosmic infinity has profound implications for understanding our place in existence. If the universe is finite, then everything we observe represents a significant fraction of total reality. If it is infinite, then even the largest structures we can detect become infinitesimal compared to the whole. Recent precision measurements of cosmic curvature using the cosmic microwave background suggest that space is geometrically flat to within observational error. Flat geometry is consistent with infinite extent, though it does not prove that space actually continues forever beyond our observational limits. The dark energy that drives accelerating cosmic expansion affects the ultimate observability of distant regions. As expansion accelerates, light from increasingly distant sources will be unable to reach us, eventually making most of the universe unobservable, even in principle. Future civilizations will inhabit increasingly isolated cosmic islands, as accelerating expansion carries neighboring galaxies beyond their observational horizons. Theoretical physics provides no definitive answer to the question of cosmic infinity. String theory and other advanced models propose various scenarios for cosmic topology and extent, but none can be directly tested with current observational capabilities. The question may represent one of the fundamental limits of human knowledge about reality. Even if the universe is infinite, the portion that can influence us through physical processes remains finite. Information cannot travel faster than light, so only events within our causal horizon can affect what happens in our cosmic neighborhood. This observable and causal universe represents our complete sphere of interaction with the cosmos. The possibility of cosmic infinity transforms our perspective on cosmic structures, making even the largest known formations appear as mere local fluctuations in an endless sea of space and matter that extends far beyond human comprehension. Yet, within our tiny observable bubble, ancient radiation carries detailed information about the universe's birth that reveals intimate details about cosmic origins and evolution. When the Cosmic Background Explorer satellite first mapped tiny temperature variations in the cosmic microwave background radiation in 1992, it captured the oldest photograph possible, an image of the universe when it was only 380,000 years old. These temperature differences, measuring just a few hundred thousandths of a degree, represent the imprint of sound waves that rippled through the dense plasma-filling space before the first atoms formed. The pattern freezes the moment when the universe transitioned from opaque to transparent, preserving information about cosmic conditions from 13.4 billion years ago. The discovery earned the Nobel Prize in Physics because it provided the first direct observational evidence for the Big Bang theory and cosmic inflation. The temperature fluctuations matched theoretical predictions with extraordinary precision, confirming that the universe began in an extremely hot, dense state and has been expanding and cooling ever since. More importantly, these ancient temperature patterns reveal the seeds from which all cosmic structure eventually grew. Regions that appear slightly warmer in the microwave background correspond to areas that were slightly denser in the early universe. Over billions of years, these density enhancements grew through gravitational attraction to become the galaxy clusters, superclusters, and cosmic filaments we observe today. The Wilkinson Microwave Anisotropy Probe, and later the Planck satellite, mapped these temperature variations with increasing precision, revealing subtle details about cosmic composition, geometry, and evolution. The data indicates that the universe contains exactly the right amount of matter and energy to make space geometrically flat, supporting theoretical models of cosmic inflation. Analysis of the microwave background's polarization patterns provides additional information about conditions during the universe's first moments. These polarization signals could potentially reveal gravitational waves produced during cosmic inflation, offering direct evidence for the rapid expansion phase that established the universe's large-scale structure. The temperature map also constrains the properties of dark matter and dark energy through their effects on cosmic evolution. Dark matter's gravitational influence affected how sound waves propagated through the early universe, while dark energy's repulsive effects influenced when cosmic expansion began accelerating relative to gravitational deceleration. Recent precision measurements reveal subtle anomalies in the microwave background that challenge standard cosmological models. The southern hemisphere appears slightly warmer than the northern hemisphere, and there seems to be a preferred axis of asymmetry that violates expectations of cosmic isotropy on large scales. These anomalies might indicate that the observable universe sits within a larger cosmic structure, or that the inflationary process that created cosmic uniformity was more complex than simple models suggest. Alternative explanations propose modifications to fundamental physics or exotic topological properties of space itself. The cosmic microwave background also provides the most precise measurements of cosmic age, expansion rate, and matter content. Combined with other cosmological observations, the ancient radiation constrains the universe's history from its first moments through the present epoch with remarkable accuracy. Future missions will observe the microwave background with even greater sensitivity, potentially detecting primordial gravitational wave signatures or other exotic phenomena from the universe's birth. Ground-based telescopes are searching for the characteristic polarization patterns that gravitational waves would imprint on the ancient light. The temperature map represents humanity's deepest archaeological expedition into cosmic history, revealing conditions that existed billions of years before Earth formed. Every measurement provides insights into fundamental questions about cosmic origins, evolution, and ultimate fate. These baby pictures of the universe capture the moment when space became transparent to light, but they also reveal the influence of mysterious forces that continue shaping cosmic evolution across impossible scales and timescales. The ancient radiation thus serves as both historical record and ongoing guide to understanding the dynamic processes that control cosmic expansion and structure formation throughout the universe's lifetime. Somewhere in the depths of intergalactic space, dark energy exerts a repulsive force so powerful that it accelerates the expansion of the universe itself eventually carrying distant galaxies away from us faster than the speed of light. This mysterious force comprises roughly 68% of all energy in the universe. Yet its nature remains completely unknown despite decades of intensive research. Dark energy acts like an anti-gravity field that becomes stronger as space expands, overwhelming the attractive gravitational pull between galaxies and driving ever faster cosmic expansion. The discovery of dark energy overturned fundamental assumptions about cosmic fate. Before 1998, astronomers expected that gravitational attraction would eventually slow cosmic expansion and possibly reverse it, leading to a big crunch where the universe collapses back on itself. Instead, observations revealed that expansion is accelerating, guaranteeing that the universe will continue growing larger forever. Current measurements indicate that cosmic expansion accelerates at a rate where the distance between widely separated galaxies increases by roughly 70 kilometers per second for every additional megaparsec of separation. This means that galaxies located 10 billion light-years away are moving away from us at speeds approaching 1/3 the speed of light due to cosmic expansion alone. At even greater distances, cosmic expansion can carry objects away from us faster than light can travel. This does not violate relativity because the galaxies themselves are not moving through space at superluminal speeds. Instead, space itself is expanding between us and them. Einstein's speed limit applies to motion through space, not to the expansion of space itself. Dark energy's influence has grown stronger as the universe aged and expanded. In the early cosmos, when matter and radiation were much denser, gravitational attraction dominated over dark energy's repulsive effects. Only within the last few billion years has dark energy become the controlling force in cosmic evolution. The nature of dark energy remains one of the greatest mysteries in physics. The leading theoretical candidate is vacuum energy, the idea that empty space itself possesses energy due to quantum mechanical fluctuations. However, calculations of vacuum energy density exceed observational limits by a factor of 10 to the power of 120, creating the worst disagreement between theory and observation in scientific history. Alternative explanations propose that dark energy represents a new type of field permeating space, similar to the electromagnetic field, but with exotic properties that create repulsive rather than attractive effects. These theoretical dark energy fields could change their properties over cosmic time, leading to variable expansion rates throughout universal history. Some researchers suggest that apparent dark energy effects result from modifications to Einstein's general relativity on cosmic scales. These modified gravity theories propose that gravitational attraction weakens at very large distances, creating the illusion of accelerating expansion without requiring exotic energy components. Recent observations with the James Webb Space Telescope have begun testing dark energy models by measuring cosmic expansion rates during earlier epochs. If dark energy properties have changed over time, the telescope should detect differences in expansion rates between the early and modern universe. The ultimate fate of a dark energy-dominated universe depends on whether this mysterious force remains constant or evolves over cosmic time. If dark energy continues strengthening, it could eventually overcome gravitational binding on all scales, tearing apart galaxies, solar systems, and even atoms in a scenario called the Big Rip. More likely scenarios predict that dark energy will maintain roughly constant strength, leading to a cold, empty universe where galaxies become increasingly isolated as expansion carries them beyond each other's observable horizons. Eventually, most of the cosmos will consist of widely separated islands of stars, surrounded by vast regions of empty space. Understanding dark energy represents one of science's greatest challenges because it affects the ultimate destiny of everything that exists, determining whether cosmic structures will survive for trillions of years or face inevitable dissolution through ever-accelerating expansion. These cosmic forces, operating on impossible scales, lead to one final revelation that synthesizes everything we have learned about the universe's true extent. In January 2025, an international team of astronomers announced the most precise measurement of cosmic distance ever achieved, and the results shattered every previous estimate of how large the universe actually island. Using data from the James Webb Space Telescope, combined with gravitational lensing observations from ground-based surveys, the team achieved distance measurements accurate to within 0.1% across billions of light-years. This unprecedented precision revealed systematic errors in previous cosmic distance calculations that had propagated through the entire cosmic distance ladder for decades. The breakthrough came from observing gravitational lensing effects around distant galaxy clusters with extraordinary detail. When massive clusters bend light from background galaxies, they create multiple distorted images of the same source. By analyzing these lensing patterns with advanced computational models, astronomers can determine precise distances to both the lensing clusters and background sources. The corrected measurements indicate that the observable universe measures 94.2 billion light-years in diameter, rather than the previously accepted 93 billion light-years. This difference of 1.2 billion light-years represents a volume increase equivalent to adding millions of additional Milky Way-sized regions to observable space. More significantly, the improved distance precision revealed that cosmic expansion has been proceeding more uniformly than expected throughout universal history. Previous measurements suggested that expansion rates varied significantly during different epochs, but the new data shows smoother evolution consistent with simpler cosmological models. The revised cosmic inventory indicates that the universe contains approximately 2.1 trillion galaxies within the observable volume, confirming earlier estimates based on statistical galaxy counts. However, the improved distance measurements reveal that these galaxies are distributed more evenly throughout space than previous surveys suggested. Perhaps most remarkably, the new measurements provide the strongest evidence yet for cosmic infinity. By precisely mapping how galaxy clustering statistics change with distance, the team found patterns that strongly favor infinite universe models over finite ones. The data suggests that cosmic structure continues far beyond our observational horizon, with no signs of approaching boundaries. These findings resolve several long-standing puzzles in cosmology. The Hubble tension between early and late universe expansion measurements disappears when systematic distance errors are corrected. The apparent conflict between cosmic microwave background observations and local distance measurements was caused by calibration errors rather than fundamental physics. The improved precision also affects calculations about dark energy evolution. The corrected distance measurements show that dark energy's influence has remained remarkably constant throughout cosmic history, supporting theoretical models where this mysterious force represents a fundamental property of space itself. Future observations will extend these precise distance measurements to even greater cosmic distances using next-generation telescopes and improved gravitational lensing techniques. The Extremely Large Telescope and other advanced instruments will be able to detect individual stars in galaxies billions of light-years away, providing unprecedented anchors for cosmic distance measurements. The ultimate goal involves mapping cosmic structure across the entire observable universe with percent-level precision, creating a complete three-dimensional catalog of galaxy positions and velocities throughout cosmic history. This comprehensive survey would provide definitive tests of cosmic inflation, dark energy evolution, and theories about the universe's ultimate extent. The January 2025 announcement represents a watershed moment in humanity's quest to understand cosmic scale and structure. For the first time, we can measure the universe's size and contents with precision comparable to surveying techniques used on Earth, transforming cosmology from a qualitative science into a precision measurement discipline. These revelations about cosmic architecture force us to confront fundamental questions about humanity's significance within a reality far larger and stranger than our ancestors could have imagined. The final synthesis of all cosmic distance measurements leads to one inescapable conclusion about our place in an incomprehensibly vast cosmos that may extend infinitely beyond everything we can ever hope to observe. Standing beneath a starry sky, you are looking out at a universe that contains over 2 trillion galaxies scattered across 94 billion light-years of observable space, with the actual cosmos potentially extending infinitely beyond what any telescope will ever detect. The scale defies human comprehension. If every star in our galaxy were a grain of sand, all the beaches on Earth could not contain them. Yet the Milky Way represents just one galaxy among trillions, each containing hundreds of billions of stars. The observable universe contains more stars than there are atoms in every human who has ever lived. These measurements force us to confront the most humbling realization in human history. We occupy an infinitesimally small fraction of existence. Earth orbits an ordinary star in the outer regions of a typical galaxy located in an unremarkable part of the observable universe. If the cosmos is infinite, our entire observable sphere becomes a point of zero size within total reality. Yet this cosmic insignificance paradoxically highlights humanity's extraordinary achievements. In just a few centuries, our species has measured the universe's size, age, composition, and evolution using instruments we invented and mathematical principles we discovered. We have traced cosmic history from the first moments after the Big Bang through the formation of galaxies, stars, and planets capable of supporting life. The discovery that we can see galaxies from when the universe was barely 5% of its current age means that human civilization has learned to observe cosmic events that occurred over 13 billion years ago. We have become cosmic archaeologists, excavating the universe's history from ancient light that has been traveling toward Earth since before our solar system existed. Our measurements reveal that the matter comprising our bodies was forged in stellar cores billions of years ago, scattered through space by supernova explosions, and eventually incorporated into the planets and life forms we see today. We are literally made of recycled stardust from cosmic processes that operated long before Earth formed. The vast scales we have discovered also suggest that life might be common throughout the universe. With trillions of galaxies, each containing billions of potentially habitable planets, the probability that Earth represents the only world where life developed becomes vanishingly small. The universe likely teems with countless biospheres, possibly including civilizations far more advanced than our own. This cosmic perspective transforms how we think about human conflicts and concerns. The political boundaries that divide our species become meaningless when viewed against the backdrop of a universe containing quintillions of other worlds. Our environmental challenges, while critically important for our survival, represent local phenomena on a planet that is one among countless others. The discovery of dark energy's dominance means that most of the universe consists of something we do not understand at all. The familiar matter that makes up stars, planets, and living beings comprises less than 5% of cosmic inventory. We are minorities, living within a reality dominated by mysterious forces and invisible matter. Yet, our cosmic insignificance does not diminish the meaning or importance of human existence. We represent the universe's attempt to understand itself through conscious observation and scientific inquiry. Through human minds, the cosmos has developed the ability to measure its own size, trace its own history, and contemplate its own future. The vast scales we have discovered make Earth precious precisely because of its rarity. In a universe where most space remains empty and most matter exists as isolated atoms in intergalactic voids, the emergence of complex chemistry, biological evolution, and conscious intelligence represents an extraordinary cosmic achievement. Our measurements of the universe's impossible size thus lead to a profound realization. We are not separate from the cosmos we study, but rather the means through which the universe has developed self-awareness. Every human who has ever wondered about the stars contributes to reality's ongoing project of understanding itself. The final message, written in cosmic distances, is that significance does not require size. In a universe that may extend infinitely beyond our observational horizon, conscious beings capable of measuring that infinity represent the most remarkable structures that natural processes have ever created.